Hello everyone, and today we'll be starting off with chapter 3, that is going beyond the basics, detecting features in images. So, in chapter 2, what we had done was we trained a model with the fashion MNIST dataset, and what we are going to do in chapter 3 is going beyond basic neural networks and learning about convolution and convolutional neural networks. So let's get started. In chapter 2, we learned how to get started with computer vision by creating a simple neural network that matched the input pixel of a fashion MNIST dataset to 10 labels, each representing a type or class of clothing. And while he created a network that was pretty good at detecting clothing types, there was a clear drawback. So, your neural network was trained on small monochrome images that each contained only a single item of clothing, and that item was centered within the image. To take the model to the next level, you need to be able to detect the features in the images. So, what are we saying here is that a major drawback of fashion in this dataset was that the images were monochrome and the main element or the clothing type that we had to guess or categorize was centered in the image. There was no other kind of object in the background or in the foreground. So it was just the main clothing item in the middle of the image. But now what we'll be going to do in this chapter is we need to be able to detect features in images. So for example, instead of looking merely at the raw pixels of image, what if we could have a way to filter the images down to constituent elements? Matching those elements instead of raw pixels would help us to detect contents of images more effectively. So let's consider the fashion MNIST dataset that we used in the last chapter. When detecting shoe, the neural network may have been activated by lots of dark pixels clustered at the bottom of the image, which it would see as the sole of the shoe. But when the shoe is no longer centered, the filling the frame, this logic does not hold. So what does it mean? That when in chapter 2 what we were doing is the main image was centered. The main shoe or clothing item, a jacket or anything in the photograph was centered. But when the shoe is no longer centered and the filling of the frame, the logic that we used in chapter 2 does not hold. So what we were doing earlier was that the neural network was activated by lots of dark pixels, and we were like, okay, these are the dark pixels and these are the ones, the values were ranging from 0 to 255. So we were saying that this is the image. Rest, the ones which are zeros, were like dark things. We did not consider that. But if the shoe is no longer centered, what will we doing? One method to detect features come from photography and image processing methodologies. So, if you've ever used a tool like Photoshop or GIMP, I guess it's called, to sharpen your image, you're using a mathematical filter that works on the pixels of the image. In another word, for these filters is a convolution, and by using these in a neural network, you will create a convolutional neural network. So in this chapter, you will learn about how to use convolutionals to detect features of an image. So we no longer depend on the pixels for just getting, we'll be pixel values, we'll just be able to detect the features ourselves using convolutional filters. You'll then dig deeper into classifying images based on the features within. So the dependency that the image or the object we're trying to classify should be in the center of the image, and it should have these many pixels, that will nullify, because now we'll be able to get get those features from the image ourselves using convolutional neural networks. We'll explore augmentation of images to get more features and transfer learning to get pre-existing features that were learned by others, and then look briefly into optimizing your model using dropouts. So let's get to what's convolutions. A convolution is simply a filter of weights that are used to multiply a pixel with its neighbors to get a new value for the pixel. For example, consider the ankle bone the image from Fashion MNS and the pixel values for it as shown. So as you can see, there is a matrix, and you can see for a pixel in white color, the value is 0 in the first row of first column. You can see the value 0 for just direct white color. Then the color goes to a little gray shade and the value turns to 64. In the next one, you can see the color is much deeper gray and the value turns to be 128. And finally, you can see that the maximum value is 226, that is the most darkest shade, or maybe turning to black shade of the image. So it makes a whole matrix. So it's a 3 cross 3 matrix. Now what are we going to do is, we are just multiplying this matrix of pixels with its neighbors to get a new value for the pixels, right? If we look at the pixels in the middle of the selection section, we can see that it has a value 192. So in the gray matrix, as we can see in the middle one, the value is 192, right? So the pixel above and to the left has value 0. The one immediately above has value of 64 that we already have discussed. If we then define a filter in the same 3 cross 3 grid. So firstly we have converted the image in form of a matrix of pixels. So all that matrix is just the value of pixels. Now what are we going to do is, for convolution, it's a convolutional filter, right? So we'll be designing a filter of 3 cross 3 grid. The filter is nothing, just another matrix which we are going to use to multiply to the pixel matrix. So 3 cross 3 from the below the original value, as you can see. So here the blue matrix is the convolutional filter. It's also 3 cross 3 because the matrix of the pixels is 3 cross 3. So we can transform that pixel by calculating a new value for it. So what are we going to do is, we are going to transform the filter matrix by calculating a new value for it. And how are we going to get the new value is, we do this by multiplying the current value of each pixel in the grid by the value in the same position in the filter grid and summing up to the total. So I hope every one of you know how to do multiply in the matrices. So how do we do that is, we take the first element of the first matrix and we multiply the first row of the pixel matrix to the first column of the filter matrix, and then we sum these all up. So as you can see that in this, while the current value of the pixel in the center of the selection is 192, the new value after applying the filter will be, here is the whole multiplication of the matrix. This equals to 577, which will be the new value for that pixel. Repeating this process across every pixel in the image will give us a filtered image. So what is this? What we have done here is that this new value that you can see in the last line, this new value belongs just to the center part of the pixel filter. So you can see the pixel matrix has a middle number as 192. We have just found a filtered value for this pixel 192, and it will be replaced by 577. That was when we calculated the matrix multiplication of the two matrices. Let's consider the impact of applying a filter on a more complicated image. So there's an ascent image that is built by SkyPy for easy testing. This is a 512 cross 512 grayscale image that shows two people climbing a stairs. So yeah, I hope this picture is clear to you. So in this, what we can see is that we are using filter to get the vertical lines. So how we are getting the filter is, there is a image, the machine will convert this image into a matrix form as we have seen earlier. So there will be a matrix of pixels that will be multiplied by this filter that's in blue matrix, and finally we'll get a image that only has vertical lines highlighted, and the rest of the things will be turned to zero or in a darker shade. So now similarly, the small change to the filter can emphasize the horizontal line. So what we have just changed is, we have earlier the middle column was 0, but in figure 3.3 we can see that the middle row is 0 zeros. These examples show that the amount of information in image is reduced, so we can potentially learn a set of filters that reduce the image to features, and those features can be matched to labels as before. So what we were doing earlier were that the pixels were depicting the features and the image was just centralized. The rest of the background was just noise. But now if we want to process any image that we take, what we can just do is we can get the features out in form of pixels, and then we can process it as the earlier one we were doing. Previously, we learned parameters that were used in neurons to match inputs to outputs. Similarly, the best filters to match inputs to outputs can be learned over time. When combined with pooling, we can reduce the amount of information in the image while maintaining the features. Now, let's talk about pooling. Pooling is a process of eliminating pixels in your image while maintaining the semantics of the content within the image. You will understand this better with the image on the next page. So, I'll show you a concept of max pooling. Here in figure 3-4, you can see max pooling. So basically what we are doing here is, we have a matrix on the left hand side that is a 4x4 matrix. Now what we are going to do is, we consider on the left to be the pixels in the monochrome image. We then group them into 2x2 arrays. So in this case, the 16 pixels are grouped into 4 2x2 arrays. These are called pools. So what we are doing here basically is that from a big matrix, we'll get 4 different small matrices of 2x2 arrays, right? Then according to max pool, we'll find the maximum value of those 4 pools. All those 2x2 arrays consisting of maximum values of 192, 144, 255, 168, we'll combine that and form a new array. So let's read ahead. We then select the maximum value in each of the groups and reassemble those into a new image. Thus, the pixel on the left are reduced by 75% with maximum value from each pool, making up the new image. So as we have seen earlier in the image of two people climbing up the stairs, that is figure 3-5, that shows the version of ascent from figure 3-2 with vertical lines enhanced after max pooling has been applied. So after max pooling has been applied to this image with vertical filter, you can see how clearly we can see the vertical lines. Note how the filtered images features have not just been maintained but further enhanced. So max pooling has helped in enhancing the features. Also, the image size has changed from 512 cross 512 to 256 cross 256, a quarter of the original size. So, there are two benefits of image enhancement using pooling. First is for that image got enhanced, that we can see in the vertical enhancement, and second, the size of the image got smaller. There's a note that there are other approaches to pooling, such as min pooling or minimum pooling, which takes the smallest pixel value from the pool, and average pooling, which takes the overall average of the pool. So if you think that max pooling it does not work for your image, you can use min pooling or average pooling. Now it's time to implement convolutional neural networks as we have created in chapter 2 for fashion feminist dataset. Now here's the code for the same. That's the same code from chapter 2, and to convert this into a convolutional neural network, we simply have to add the convolutional layers, also the pooling layers. So we'll see that in a bit. As here you can see, to implement a convolutional layer, you'll use tf.keras.layers. That's the same as we have already seen. But there is a type of layer called con2D for convolutional layer. This accepts as parameters the number of convolutions to use in the layer, the size of the convolutions, the activation function, etc. For example, here's a convolutional layer used as the input layer to a neural network. So how's the code written is tf.keras.layers con2d 64 the number of convolutions, 3, 3 the size of convolutions, the activation function that is relu here, and the input shape that is 28, 28, 1. So as 28, 28 we have already seen. What the 1 means we'll understand next. In this case, we want the layer to learn 64 convolutions. It will randomly initialize these, and over the time, will learn the filter values that work best to match the input values to the labels. Right? The 3, 3 indicates the size of the filter we've already discussed. Earlier, I showed 3 cross 3 filter, and that's what we are signifying here. So, the shape or size of the filter can be any odd number and is typically an odd number, and you can change it to any one. So usually it is like 5 cross 3, 3 cross 3, 7 cross 7. So because of how the filter removes the pixel from borders of the image, as you see later. Activation and input shape parameters are the same as before, but earlier we were using the size, the input shape as 28 cross 28. Now we are using 28 cross 28 cross 1 because the con2D layer are designed for multicolor images. We are specifying the third dimension, that is 1. So 1 signifies the third dimension because the color images have 3 parameters, that is RGB. It's stored in RGB values to make a complete multicolor image. Here's how the use of pooling layer in neural networks. So we'll see how we write the code for pooling. So it's same as tf.keras.layers, goes the same. Then we use max pooling 2D because it's a 2D array, and then it's 2, 2. In the example, you can see example figure 3-4. We split the image into 2 cross 2 pools and pick the maximum value in each. This operation could have been parameterized to define the pool size. So we'll see how the new code will be written with all those pooling layers and the convolutional layers in it. So we'll go through this code one by one and we'll write it simultaneously in our Colab as well. So here's a code. The rest code was same. Just one thing has changed, that there was the same that we imported TensorFlow, we got the data, we divided it. The reshaping of the images is that 60,000, 28, 28, 1 because multicolor images. Then normalization by 255. Here's the model, was how model is defined is that con2D layer goes first, then max pooling, then again another convolutional 2D layer, then a max pooling, then a flattened layer, and finally 2 dense layers. And the rest goes same for as before. There are few things to note here that we'll understand while we write the code. Now let's understand what the code before what we have seen means for. So we'll be understanding what this whole code here means for, right? So there are few things to note here. Remember earlier when I said that input shape for the images had to match what a Con2D layer would expect. So that's why I updated it to 28 cross 28 cross 1, because the input data has to be shaped accordingly to the image and the layer that we are giving the input to. So say for example, you have a rectangular input but you are passing a circle. There is a chance that it might enter, but there is a maximum probability that a circle won't fit in a rectangle, right? So same here is that in a Con2D layer, we have to give the same input shape and size to the layer as it expects. The data also had to be reshaped according to 28 cross 28 in the number of pixels in the image, and 1 is the number of color channels. You'll typically find that this is 1 for a grayscale image or 3 for a color image, where there are 3 channels. So we are using 1 right now, that means it's a grayscale image. But if we are using 3 there, that means it is a RGB colorful image with the number indicating the intensity of that color. So prior to normalizing the images, we also reshape each array to have that extra dimension. The following code changes our training data set from 60,000 images each 28 cross 28 to 60,000 images each 28 cross 28 cross 1, right? So before normalizing the images, we have to reshape it according to the kind of filter or the kind of layer we are using. Training images are reshaped here, as you can see. Then do the same thing for the test dataset, because test and train both be entering that same input. Also note that in the original deep neural network, DNN, we ran the input through a flattened layer prior to feeding it into first dense layer. We've lost that in the input layer here. Instead, we just specify the input shape. Note that prior to dense layer, after convolutions and pooling, the data will be flattened, because see, the convolutions input needs to be 28 cross 28 cross 1, but the input of the dense layer needs to be 28 cross 28. That's why we need to use a flattened layer between the convolutional layers as well as the dense layer, because each layer needs different kind of input and we have to manage our data specifically according to the input needs of the layers. Training this network on the same data for the same 50 epochs as the network is shown, we can see a nice increase in accuracy. The previous example reached about 89% of accuracy with 50 epochs, and this one will hit 99% in around half that many 24 or 25 epochs. So we can see that adding convolutions to the neural network is definitely increasing its ability to classify images. So the accuracy we can see rises from 89% to 99%. Let's take a look at a journey an image takes through network, so we can get a little bit more of understanding of how this works, right? Exploring convolution networks. You can inspect your model using the model.summary command. So we'll run this command model.summary. So when you run it on the fashion MNIST convolutional network we've been working on, and you'll see something like this. So model sequential Layer type, output shape, parameters, right? So it shows the type of layer, it shows the shape of output it's giving, and the parameters, number of parameters it takes. So the first layer is Con 2D and it has the output shape of 26, 26, 64 and the parameter it has is 640. Next comes the max pool 2D layer which has the output shape of this 13 cross 13 cross 64. Next, the convolutional layer gives 11 cross 11 cross 64. Then the max pool layer gives the 5 cross 5 cross 64. The flattened layer flattens all down into 1600 parameters only. The dense layer takes that and outputs 128 parameters. And finally, the dense network, the last one, gives the 10 outputs only. So what happens here is, as we know in fashion numbers, there are only 10 labels. So in the last layer, we just get 10 labels, as you can see. Right. Let's first take a look at the output shape column to understand what is going on here. Our first layer will have 28 cross 28 images and apply 64 filters on them. But because our filter is 3 cross 3, a 1 pixel border around the image will be lost, reducing our overall information to 26 cross 26 pixels. Right? So, as we can understand that, see, there is an image in the first layer. We have 28 cross 28 images, right? Let's consider one image that is 28 cross 28. You apply 64 filter. You apply one filter to that is 3 cross 3. So what happens is that 1 pixel will be lost because the border is not taken. Just the middle part is taken in a 3 cross 3 in a 3 cross 3 filter, right? So what happens if you take all those images together, that is 20 cross 28 images, the overall information will be reduced by 26 cross 26 pixels, because in each iteration there will be the border pixels will be lost, because that's how the filters work. If we take each of the boxes as a pixel in the image, the first possible filter we can do starts at the second row and second column. The same would happen on the right side and at the bottom of the diagram. See, as you can see in this pixel here, you can see in the figure that the middle pixel only gets the selected. Only the middle pixel. You can see the cross over here, that all the pixels on the borders, they are not taken into the consideration because of the filter. It's the habit of the filter. We can see that it loses all these pixels on the border. Thus, an image that is A cross B pixels in shape, when runs through 3 cross 3 filter, will become A minus 2 cross B minus 2 pixels in image in shape. Similarly, a 5 cross 5 filter would make it A minus 4 cross B minus 4 and so on. We are using 28 cross 28 image and a 3 cross 3 filter. Our output will now be 26 cross 26, because we are using a filter here and the filter crops out the edges as well as the border pixel. After that, pooling layer is 2 cross 2. So the size of the image will half on each axis, because as we have seen earlier in pooling, the pooling layer, what we do is we get number of pools. So 2 cross 2 image arrays will get in one pool, right? And we'll be finding the maximum value of each of those pool and we'll be creating another one. So there the image size would be half, as we have seen earlier. Then become 13 cross 13. The next convolutional layer will reduce this further to 11 cross 11, and next pooling rounding down will convert the image into shape of 5 cross 5. So by the time image has gone through 2 convolutional layers, the result will be many 5 cross 5 images. Many how? How many you would say? So we can see that In the parameters column, you can already see using order.summary that we got in the parameters column, we'll get how many 5x5 images we get. Each convolution is a 3x3 filter plus a bias. Remember earlier with our dense layers, each layer was y is mx plus c, where m was a parameter or weight we can say, and c was our bias. This is very similar concept, except that because the filter here is 3x3, there are 9 parameters to learn. Given that we have 64 convolutions defined, we'll have 640 overall parameters. Each convolution has 9 parameters plus a bias, so there are a total of 10, and there are total 64 convolutions, so 64 multiplied by 10, there will be 640 overall parameters. Next, the max pooling layers don't learn anything. They are just here there to reduce the size of the image. So there are no learned parameters, hence the 0 being reported. This is important, that max pooling layer just reduces the image size and it has nothing to learn. The next convolutional layer has 64 filters, but each of these is multiplied across the previous 64 filters, each with 9 parameters. We have a bias on each of the new 64 filters, so our number of parameters should be 64 cross 64 cross 9 plus 64, which gives us 36,928 parameters the network needs to learn. If you are confused in this, let's go through this one by one in a step format, right? So there are 64 convolutions, but each of these is multiplied across the previous 64 filters, which each had 9 parameters. So 64 filters had 9 parameters, means 64 multiplied by 9, and this 64 multiplied by 9 is applied to 64 filters. So we multiplied 64 again with that. Then it says we have a bias on each of new 64 filters. So we add 64 to that. So it actually becomes mx plus c. So it gives us total of 36,928 parameters. If this is confusing, try changing the number of convolutions in the first layer to something, say example of 10. You will see the number of parameters in the second layer becomes 5,824. It's same as the above. By the time we get through second convolution, our image at 5 cross 5, and we have 64 of them. If we multiply this out, we now have 1600 values, which we'll feed into a dense layer of 128 neurons. Each neuron has a weight and a bias, and we have 128 of them. So the number of parameters the network will learn is 5 cross 5 cross 64 cross 128 plus 128, giving us 204,928 parameters. Our final dense layer of 10 neurons takes in the output of previous 128. So previous 128 multiplied by 10 plus the 10 it's learned in this one. So it's added to 10. Gives us 1290. The total number of parameters is then summed to 24376. Training this network requires us to learn the best set of these all parameters to match the input images to their labels. It's a slower process because there are more parameters. So I can tell you in advance that our convolutional neural network model will run really slow because there are lots and lots of parameters, as we can see over here. There are these much of parameters. As we can see from the results, it can also build some more accurate models. Of course, with this dataset, we still have the limitation that the images are 28 cross 28 monochrome and centered. Next, we'll take a look at using convolutions to explore a more complex dataset comprising color pictures of horses and humans, and we'll try to determine if an image contains one or the other. In this case, the subject won't always be centered in the image, like in the fashion amnest, and we'll have to rely on convolutions to spot the distinguishing features. So we'll read about that in the next video, but now we'll just go through the code and we'll write it and run in our Colab. So here's the code for the chapter 3 until till the point we have read. So here is, let's get started. So first we'll import TensorFlow as TF and all the basics import that we've already done. This whole code will be available in the GitHub and the link would be in the description. Then we have imported sequential and dense. Then we've got our data, fashion amnest using tf.keras.datasets. Finally, we have separated our image in training images, training labels, test images, and test labels. We've loaded the data. We have reshaped our training images in 60,000 28 cross 28 cross 1 shape because that's the input for Conv2D, and then we have normalized the images as well. Then we have also reshaped our test images similar to the training images and normalized them as well. Now it's time for our model. So here is our model, that is tf.keras.sequential, tf.keras.layers.conv2d, our first layer with activation value and input shape of 28 cross 28 cross 1. Then the second layer, that's the max pool layer. Then the third layer, that's con2d layer again. Then max pool layer again. Then flatten layer because our dense layer won't accept the output shape of the max pooling layer. So that's why we have to flatten our image because the dense layer does not accept the same output shape as of the max pooling layer. So then we have two dense layers. We'll compile the model with optimizer as Adam and loss sparse categorical cross entropy, and finally the matrix of accuracy. Then we'll model.fit training images, test images for evaluation with 50 epochs. So as I've told you earlier, I've run this before and I can say that it will actually take a lot of time, but as you can see from my previous run that the accuracy is pretty good. You can see 99% accuracy here at just 26 epoch, right? So let's run this again, and here you can see it's downloading the data for training labels, training images, test labels, and test images. And it's taking quite a time for just first epoch to run. So it will take some time because it's a big data and we are actually parsing 60,000 images at once. So you can see that 60,000 images are passing at the same time. So it will actually take some time. So let's take a short break here and we'll return to this video when the whole running process with 50 epochs is done. Now that our epochs have finally completed, we can see that about 99% of accuracy is reached on the 26th epoch itself. The training has been completed and the final accuracy is about 99.48%. For the prediction, we can see that the model has predicted with the maximum value to the last label with 1 into 10 to the power 0. For the rest, it has given 10 to the power minus 31, minus 23, minus 36, which is far more better than for the previous model as we have seen before. Here you can see model.summary that we have also seen in the book itself, where we can see the layer, the output shape, as well as number of parameters in the each layer. So as we know that the pooling layer does not have any parameters because it's simply reducing the size of the image. Simply the next convolution layer as well as the second convolutional layer can also see the number of parameters. for the flattened layer, it also does not have any parameters because its option is to just change the input shape so that we can enter the input next to the dense layer. And finally, we can see the total number of parameters and the trainable parameters as seen here. Now we're done with the half of the chapter, and we'll stop the video over here and we'll continue with the rest of the chapter in the next video. Since the chapter is quite large, so it's better to break down the chapter into pieces so you can understand and grasp better. So if you have any doubts, please drop it in the comment section, and do check out the code for this chapter 3 in the GitHub. Thank you.